On to question 10. And question 10 says, diagram below is drawn to scale. And it shows a circle with center O, and the points A, B, and C are on the circumference of the circle. It says EAF and EDG are tangents to the circle, and tangents to the circle at A and D respectively. Then it gives us two angles that are on the diagram. Then it's going to ask us to calculate some angles. Calculate given reason for your answer, angle ACD. So first thing to find angle ACD. Angle ACD. So I like to identify that region first. Angle ACD is this angle. This angle right here is angle ACD. All right. So let's see how we can tackle that. Now, first and foremost, they told us that EG is what? EG is a tangent to the circle, and OD is a radius. The angle between a radius and a tangent is 90. Angle between radius and tangent is 90. So what does that mean? What is that telling us? That is telling us something very important. That is telling us that the angle right here, that angle right here is 90 minus 18, which is 72. So this angle right here is 72. This angle in there is 72. All right, so that's a very important bit of information. The next important information to help us to find this angle right here is that it tells us that O is the center of the circle, and so AO and OD are radii, and so the angle here and the angle here are equal. So this angle here is going to be 180. 180 minus 114 divided by 2, so that's 33. And this angle is also going to be 33. Now look carefully now, look carefully now. This angle together is 33. Not just this piece. It's all of this is 33. Just to make that clear, all of that is 33. All right. So now we know that all of this is 33. Okay. We know that this piece right here is in the green. This is what we want to find, which is 18 degrees. Now, it probably is easier if we find the small piece, so we can know this piece, and then we can subtract from 180 to get this little piece right here. So come find this inner piece. In order to find that inner piece, what I notice is that AE and ED are equal in length because of what? They're equal in length because it is a, what is the word I want to use? AE and ED are equal in length because EG and FE are tangents from the same external point. And so what is it that we're saying then is that if this is 33, right, then we know the angle at D. We know the angle at D. The angle at D is going to be, the angle at D is going to be 57. And if the angle at D is 57, 57 plus 33 is 90, just to make sure. 57 plus 33, yes, that's 90. And so this angle right here is also 57. All right. Now back to this now. Now, 57 plus all of this is 90. Ah, we get the answer now. There it is. There we go. So if all of these angles, so what am I saying? Let me write it down. So angle, so what I'm saying is 90 is equal to angle OAC plus angle CAD. CAD are angle CAD plus 57, right? That's what we know. At 90 is equal to OAC plus CAD, and they're equal to 57. So in reality, what we're saying is 33 is the sum of the angle between OAC plus CAD. OAC plus CAD is 33. All right, that's one thing that we know. We know that OAC plus CAD is 33. All right, good. What's the next thing now to find this small piece? Now, the next little information that we know is that since the sum of those two pieces is what, 33? All right, no problem. We know that the sum of these two pieces are 33. And we know that 57 and 72 give us the angle at D. So we're in this triangle right here. In this triangle, we need to find this. Is that so 33 is OAC plus CAD. And I know that right here, opposite angles in a cyclic quad is 180. All right, so these two angles, the 33 plus the 72, that give you 105. And so this angle at B is going to be 75. Opposite angles in a cyclic quad are 180. I'm going to come back to finding this angle, all right? Let's see if I can work out the others and come back to it. It doesn't matter the order in which you answer them. Angle AED. Angle AED, this angle here is going to be 66 degrees. All right. How do I know that it's 66? 57 and 57 is 114. 180 minus 114 is 66. All right. So let's give them the reason now. So we can tell them that AED is isosceles. The triangle AED is isosceles since AE is equal to ED, and angle ADE is equal to angle DAE, which is equal to 57, and then angles in a triangle sum to 180, and so AED is equal to 180 minus 2 times 57, and that's how we get 66 degrees. All right, so that's angle AED. All right, don't worry if I'm going to come back to ACD. I'm just working that one and see if I can work my way back to it. All right, and remember I said opposite angles in a cyclic quad sum to 180. So let me see what's going to come up here. I know that this in here is 33 plus this angle. I don't know what this is. This is angle BA, call it BAO. So I know that angle BAO plus angle OAD, angle BAO plus angle OAD plus, this is now angle BCD plus angle BCD. I know that those three must equal 180. These must equal 180. Because opposite angles in a cyclic quad sum to 180. And I know what is angle OAD. Angle OAD, I know that angle OAD is 33. All right, so we're going to use that somehow to come back and find this. All right, somehow we're going to work back to ACD. Oh no, OAC plus CAD is 114. So let's see. Angle ABC, ABC. So I'm going to write down this one again. Angle ABC is equal to 75. And this one is because opposite angles in a cyclic quad sum to 180. Opposite angles in a cyclic quad equal 180. And so a angle ABC is equal to 180 minus the 33 plus the 72. All right. And then they want angle OAC. They want angle OAC. Oh no, OAC plus CAD is 33. Angle CAD, that's 33. All right. Know that the sum of these two angles is 33. And we know, let me see, which formula are we forgetting? Let's look back at the theorems. Angles in a semicircle won't be applying. Angle at the center is twice the size of the angle of the circumference when subtended by the same chord. Angle at the center, let's look right here. Oh gosh, angle at the center is twice the size of the angle at the circumference when subtended by the same chord. This angle should be fifth a half of this. This is so easy, man. Can't believe I forget that one. So this one right here should be 57. Angle at C is 57. Angle at the center is twice the size of the angle at the circumference when subtended by the same chord. Nice and easy, soft. So we can write that down. We didn't even need to do anything. Angle ACD is equal to 57 degrees, and that's because angle at the center is equal to twice the size of the angle at the circumference. All right, this is because angle at center is twice the angle at the circumference, and that is of course when they're subtended by the same chord. All right, easy. And now we're basically done, because if this one is 57, we know this is 105. 57 and 105 is 160. If that is 160, then this little piece is 20. And then if this little piece is 20, then this angle is 13. So angle OAC is equal to 13 degrees. Angle OAC equal 13 degrees. Why is it 13? Because set it around here. 33 is OAC plus CAD. That's because 33 was equal to angle OAC plus CAD. But we just found that CAD is 20. And so what we're getting now is 33 minus 20, and that gives the angle OAC. Nice and easy. All right, so again, you just need to remember these circle theorems, all of them. Angle at the angles in a semicircle is 90. Angle at the center is twice the size of the angle of the circumference. Angles in the same segment from the chord are equal. Opposite angles in a cyclic quad is 180. All of these stuff. Need to remember these basic rules. All right, now we're done that. Part B. All right, so now we're looking at part B. I give you this diagram that says it's a cuboid. And it gives us something about the cuboid, and they say a straight adjustable wire connects R to P along the top of the cuboid. Calculate the length of the wire RP. So we want to calculate the length of the wire RP. To calculate the length of the wire RP, this would be the length of the wire if you hold it out straight. Right, if you just hold out the wire straight, like that have to be the length. Think about it, because you can't really like, yeah, like if you just hold out the wire straight, the straight distance from R to P will give you the correct length. All right, now we know that PQ is what? So you can't just add QR and PQ and get RP. No, because that are longer than PR. Think about it. You have one piece of wire, right? You can bend it and twist it and all of them stuff there, but the correct length when you hold it out straight. So PQ, which you know is 100. So now we can find what is PR. So PR look like, we're gonna have to use, let me see, PR look like the hypotenuse, and the hypotenuse is the square root of the opposite square plus the adjacent square. So 100 square plus 60 square, and that will give you PR. All right, so that will give you the length of PR. 100 square plus 60 square. And then you square root that, you get, it's set to 1 decimal place, so that looks like 116.7 centimeters. Then it tells us that the connection at P is now adjusted and moved to T. The connection at P is now adjusted and moved to T. Calculate the length of RT. So again, anytime you want to calculate the length of a wire, you need to just hold it out straight. So we want to go from here, so with RT, it's not here, so we want to go from here, so to here, so. Let me use a different color. This will color blind me. Let me use a different color. Let's go with true blue. That's gonna be the distance RT. So how we gonna find that now? Distance RT. All right, so we need to know the vertical distance and the horizontal distance across. All right, going from R to T. All right, the connection is now moved to T. Connection at P is moved to T, so drag it down by 20 centimeters. All right, so if we pull it down by 20, so pull it down by 20 centimeters. And so if we pull it down by 20 centimeters, then what is that telling us? Pull it down by 20 centimeters. I think I need to break this out into another diagram just to make it a little easier to visually see what's going on. It's always good when you have a cross-sectional view. If I look at it this way, I won't see what's going on. So I'm going to look at a cross-sectional view. So I have, this is P, this is T, This is just a cross-sectional view, guys. This is P, this is T. I have, this is R, and I have, this is RT. This is gonna make it look better for me now. Yeah, this look good now. This look good? Yeah. So PT is 20. PR, which we just find, is 116.7. So I'm going to use Pythagoras Theorem again. And so RT is just equal to the square root. Guys, when you look at it, always try to draw a cross-sectional view of what is happening. You see, when you're looking at cuboids, cubes, prisms, it's good when you have a cross-sectional view to do what you want to do, because sometimes the whole thingy might blur you from seeing what you need to calculate. So this is just 20 square plus 116.7 square. They square root it. Draw the cross-sectional view. It works out better that way. So when we do the cross-sectional view, what we're getting is RT is, you work that out. So that's 20 square plus 116.7 square, and you square root it. That's 118.4. 118.4. 118.4, and that's in centimeters. That's RT. Calculate the angle TRV. Again, guys, I am always of the idea to just draw a cross-sectional view. Calculate the angle TRV. TRV. So I always like to just look at a triangle, TRV. I know what is TR in length. TR, then I have RV, then I just need VT. All right, so this is T, this is R, and this is V. And what they want is angle TRV. TRV is this angle. In order to find this angle, what do we know? We know RV is 20. We know RT is 118.4. And so this looks like we have adjacent and hypotenuse. So when you have adjacent and hypotenuse, you use cosine. So we know that the cos of theta is equal to the adjacent of 20 over the hypotenuse of 118.4. And so theta is then going to be cos inverse of whatever that is, cosine inverse of whatever that is, 20 over 118.4. 20 divided by 118.4, 0.16. So it's cos inverse of 0.16, 0.169, and you take cos inverse of that, and I'm getting 80 degrees, 80.3 degrees. That's what I'm getting, 80.3. TRV. This angle, so it's adjacent over the hypotenuse. That's what I'm getting, 80.3. Now it says complete the following statement. The size of the angle through which the wires move from RP to RT is the size of the angle through which the wire moves from RP to RT. Wire moves from RP to RT. The size of the angle through which it moves from RP to RT. Oh, that's bearing. Okay, that's a nice one. So that's bearing they're asking you right here. The size of the angle that it moves from RP to RT. So it's moving from, look for the word from. So the from word is from P to T. From P. So you measure the bearing from P to T. That's 90 degrees. So right here, so that's 90. So this is 90. And it's an angle which is the same in size as RTV is. An angle which is the same in size as RTV, RTV. This is RTV. What is equal to RTV? RTV. The size of the following, we know this is 90, an angle which is the same in size as RTV. So we want something with the same angle as RTV. RTV is this angle between here. RTV, this angle. Now which angle is the same as RTV? The same as RTV. RTV is TRV. RTV. RTV is this angle right here. This can be the same as it. RTV and RTP. Something along here is going to have the same angle. So we want something with 118 and 20. 118 and 20. 118 and 20. So something with the same angle is going to be, let me look back at this again. This is something with the same angle as RTV, RTV, and something over here is going to be R. This look like, where's RTV? RTV is this big angle right here, so. And that looks like RPT. RPT, which is in triangle RPT, that is RTP, RTP. And I can justify it. If you were to find RTP, RTP is going to be cos inverse of 20 over 100 and RTP. Yeah, that's RTP. RTP.